classification, I think we just we understood the concept and the theory, and we were just trying to use the data set of city scanner. And in NIME, we are building the pipeline for decision tree, and that's where we stopped. Okay. Um, so we will continue with that. So we'll first create the classification algorithm on NIME using decision tree, and then we will use what is called today vibe coding. I don't know whether you have heard about this term called vibe coding. It is becoming very, very popular. Anybody heard about the term called vibe coding? VIBE, vibe coding? Yes, no? Did I mention to you before? No? Okay. So vibe coding is a new, you can say technique, okay, new technique that has become very popular, which basically means that you use prompt engineering to generate codes. What we have been doing what we did in Google Colab. Okay. These days there are tools like Lovable and Replit and various other tools, where actually you can build a full-fledged app just by including a database, a user interface, okay. But just by writing prompts. For example, I can just write a prompt saying that, okay, make me a e-commerce website for selling shoes. Okay. And it will make the entire thing. Okay, I don't have to worry about anything. Magic. So that's the level of generative AI. The penetration of generative AI. Okay. So that technique is called vibe coding. So that the focus is shifting, or the expertise is shifting from knowing the syntax of the code, which is the code strength of a programmer or a classical coder. So how is a classical coder different from a normal business user? The classical coder can understand the language of the computer and write the commands in that syntax. That is the strength, right? But now, if you know the business, if you know your requirement, that syntax is not required. All that you have to do is to articulate your requirement in plain English, or most of these vibe coding platforms are in English today, but I at least don't know of any vibe coding platform that has come in Indian language, but I'm sure this will come up. So that means that intermediation, I always say that the coders were like Purohits, okay, Panditji. So between lesser mortals like us and the God. Okay, so that Purohits now are not required, because now we can directly talk to the computers in our own language. So that's the kind of transformation that we are talking about. So anyway, we are actually using vibe coding when we are writing prompts in Colab Notebook and generating code for any of these algorithms. So we'll use the same model and do the same thing using Colab. Okay, and as I said, that after today's session, hopefully we'll be able to finish these two things today. Otherwise, definitely next class, I will then give you the project. Okay? Because the project will be on some of these like regression and decision tree, and there you have the flexibility of using either NIME or using Colab Notebook, using vibe coding. Any one approaches you can take to solve the problem. So obviously the data set will be different from the data set that we have been using. Okay. So far, fine, everybody? Yes, no, all good? Yes, okay. So let's go to NIME. Only thing is that I am using a different computer. So I think we did few steps last time, only a few. So I don't have that computer where I save those steps. So we will do it from the beginning. I think that also will kind of act as a little bit recap. Okay. So here we are. So we are going to create a new workflow where we are talking predicting failure. Okay. So first few steps are very similar to what we did in logistic regression. So first is we are going to read the file. I think the file is a CSV file, if I remember correctly. Let me pick up the file. No, we also have an Excel file. So let me take any one of them, Excel or CSV. Just give a second. So that I have the. Yeah. So Excel reader. Read the file. Everybody is able to see my screen? Yes or no? Okay. So do you remember any transformation that we need to do with this data? Anybody? Any transformation that is required before we can proceed? No? So two things. First of all, the outcome of our decision tree has to be a categorical value. Uh, so first of all, what is the outcome in our case? What is it we are trying to predict? Anybody?
It is scanner fail or not.
Machine fail or not. So this, as we see, NIME has read it as an integer. And it's we know why it has taken as an integer, because the data set does not say machine has failed or not failed. It just says 1 or 0. So it thinks is an integer, but 1 and 0 only represents a state of the machine, failed or not failed. So we need to change this into a string character. It's a categorical value rather than a numeric value. That's one transformation that we have to do. We also have to see if anything else like this are there, where the NIME would have considered this as a numeric value, whereas actually it's a categorical value. Okay. So here, for example, I don't see any other value, but there could be. For example, sometimes what happens is that apart from, so it's not necessary that only the transformation will be required in the output. Let's say if there was a field like city tire. So city tire can be written as 1, 2, 3. And it's possible that NIME uh, will consider them or read them as numeric value. Okay. But actually, it's a categorical value. In that case, we need to transform this from a categorical to a string. Okay. Now, before we go forward, a little bit of digression. Okay, from from understanding of predictive analytics from a business perspective. See, we have got this data as given, right? Now, suppose this is something that you are starting as a new project in your organization. You want to predict the failure of your washing machines. Okay. Based on certain features. Here, the features are given to us. Okay. But in a scenario where you have just identified an opportunity. So first of all, when you say that I want to predict whether a washing machine is going to fail or not, based on certain features or factors, that is a business opportunity that you have identified. Okay. Based on this business opportunity, the features that is likely to affect the failure of the machine, washing machine, need to be identified. Who will identify this and on what basis? Have you understood, or have am I clear with the question? Yeah, am I clear with this question or no? Shall I repeat my question, because the question is little, I might not have communicated clearly. But it's a very important question. Yes or no? Is everybody clear with the question?
Yes, yes.
Okay. So in such a scenario, how, what is the process by which you first will define the features on which the machine failure will depend? Who decides that and how is it decided? Because many times in when you are in an academic environment, you assume certain things as given. We have assumed that this data is given to us, and we are kind of, all the discussions are around how do we build a model around the data. But I want to go a step back, where I want to, we want to discuss how do we define that. Somebody has to say that ambient temperature might have an impact on the machine failure, or vibration might have an impact on machine failure, or voltage variation might have an impact on machine failure. Only if you have identified that, then only the question of collecting the data comes in. Who is going to identify that?
Correlation matrix.
Sorry?
Correlation we have to do.
No. Correlation will come to validate your assumption. Okay, so you have assumed that there is a relationship between. We'll come to the correlation. Actually, it's the p-value, because correlation by itself will not give anything, because correlation will give a number. That whether that number means that there is a significant impact or not, that will come from the p-value. But we'll park that for question for the time being. Very important question. We have to answer that question later on. But first, somebody has to say that voltage fluctuation is likely to have an impact on machine failure, and then only he will decide that we need to collect this data. This data has been collected, right? Maybe months or years. Only then able to run a machine learning model. Data cannot run. So even before I decide to run any models, you have to decide what values I need to capture. Am I making sense? Yes or no?
Yes, understood.
Okay. Making sense? Yes or no?
Yes, yes.
I'm asking a very, very important question. This is something that the question means concept, which you as business users need to know. This will not be understood by a data scientist or IT guy. This input will not come from a data scientist and IT guy. This is an input which you as business user has to give. And after this discussion, you can reflect that in those cases where your department is using any machine learning model, some of you said that you're using or you're at least planning to use, whether such inputs have been taken from you. If it is not, then there's a big problem. There's a gap. And that is what you have to go back and tell your organization, look, have you taken this input from us? If you have not taken that, you have started at a wrong point. Okay. So the first step, if I look at the whole process, and subsequently, once we have covered these concepts, I'll tell you the whole flow. What are the processes? What are the steps which an organization has to go through to create a machine learning model? We'll discuss that once we have gone through the initial building blocks. But the starting point is, I need to identify. First, the starting point obviously is opportunity identification. That means I need to know that, or I need to somehow justify that, yes, I need to predict machine failure. If that requirement is not there, that business requirement is not there, then obviously the whole thing, there's no question of pursuing it. So there is a economic value in predicting whether the washing machine is going to fail or not. That's the opportunity identification. Once I identify the opportunity, before I collect the data, I must identify what are the likely factors on which the machine is likely to fail. Correct? Who does this? Who will do this? Who will say that radiation is likely to have an impact or radiation leakage on machine failure, and hence this data should be collected? Who will do this?
Domain expert.
Sorry?
Domain expert. Domain expert.
Domain expert, the engineer. In this case, the core engineering team, which some of you belong to, the core design team, who knows the machine, they have to identify. And that is why it is very important for you to understand this, because if you have not identified, if means you means need not be you as an individual, as a person, as a department. If the domain experts have not been consulted to collect the data, then there's a gap. Okay. So first question. Second question. There can be three things. One thing is that the domain expert says that, yes, I know radiation leakage determines the machine, whether the machine is going to fail or not. But I know exactly that if the radiation leakage, whatever the unit of measure is, if the radiation leakage, let's say it's percentage or something like that, I don't know what measure. If the radiation leakage is more than 10%, it will definitely fail. I know the exact condition when the machine is going to fail based on radiation leakage. What impact will it have in collecting the data about radiation leakage and building or putting radiation leakage as a feature in building the model? Do you think radiation leakage will play a role in building this model, or rather will play a role in or will be used to collect the data and build a model? Yes or no? Am I making sense? The engineers say that I know that if the radiation leakage is more than 10%, the machine is surely going to fail. I have a formula, I have an engineering formula. We all know what kind of engineering formulas are there. Okay, various kinds of formulas, thermodynamics, etc. Okay, I've forgotten all of them, but you are doing engineering work, so you will know. And there's a formula which says that based on the radiation leakage, the machine is or not. And in fact, we design them in such a situation, would you still insist on building a in the model feature and it's going to fail or not? Yes or no? Yes, guys. I need a simple yes or no answer. Again,
Yes.
if the question is not, let me know. Yes means we are still going to build
Yes.
the model.
Yes.
The answer is no. Answer is no. No. Because if I know engineering formula, why do I need the data? The formula is established by scientists, by engineers. I just need to measure the leakage by a sensor, and if the moment I see that the leakage is greater than 10%, immediately I'm going to stop the measure. What you're working for to do? The temperature go up, sounding it trips. Or electricity goes up, the current goes up, it trips. Voice is breaking. Uh, 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 open. So let's see. I use the camera probably to get a better branding. Okay. Okay, so if I know that there is an engineering formula based on which I can determine whether the machine is going to fail or not, there is no case for building any model. Is this clear? We discussed this. There is an engineering or physics-based method of prediction, and there's a data-based method of prediction. Physics-based method of prediction is used by engineers when there is a defined y equal to fx. I know the function x. I not only know that y depends on x, I know exactly the formula which will give me the value of y based on x. And this formula has been established by scientific research or engineering research. Such cases, I do not need any machine learning model. That's the gate. Again, as domain experts and engineers, you have to decide whether there is a case for machine learning model or not. If you think that there is an engineering formula existing which can predict machine failure based on radiation, you will say, assuming that radiation is the only factor, you will say that there is no case for machine learning model, no need for any data scientist to do any job on this. We are the engineers, we know when the machine is going to fail. Clear? Yes or no? Are we clear? Yes or no?
Yes. Yes.
Okay, great. Okay, so but when we are going to say that I will go pass it on to the data scientist to build a machine learning model, when as an engineer I know that there is a linkage, or I not know, but I have a hypothesis, or I have a hunch or an intuition or experience that if there is a radiation leakage, the machine is going to fail, is likely to fail. But I don't know the exact formula. I don't know what percentage of radiation leakage beyond which it will fail. I know there's a relationship, but I don't know the exact, cutoff. Then I will consider radiation to be one of the features to be used to predict whether a machine is going to fail or not. So you have, as domain expert, you have to identify these set of features, which is shown over here. You have to identify this set of features. What are the features that are likely to affect the machine failure? Now, some of you mentioned about correlation. Where will the correlation come from? You have assumed that radiation leakage will affect machine failure. You know there is a dependency, but you don't know the formula. There is probably not enough engineering evidence or formula on that. After you are, while you are building the model, you are finding out the correlation. Then you figure out that whether radiation really has an effect on the machine failure. That is where the p-value comes in, where you are validating your assumption that yes, we assume that radiation has an impact on machine failure, and it really has an impact, or it doesn't have an impact. So far, fine, everybody? Yes? Are we all good? Yes or no?
Yes, yes.
Great. So as of now, we have the transformation and we change this machine status to string. This. Okay, so we have the output. We have the statistics. In this case, we don't have any missing values, so kind of we don't need to do any pre-processing. Okay, as far as missing values is concerned, and we can directly go to EDA. So some of the EDA that we did was, I'm just repeating these steps. We did it last time. We did a box plot. And do a box plot of radiation leakage. Similarly, you can do a box plot on all other numeric measures. In the box plot, we can see that there are maybe a couple of outliers which are just lying outside the viscous. In real scenarios, we have to treat those outliers. Maybe if these outliers are not belonging to the positive and the rarer class, either positive or negative, we will probably remove them. If we have a class imbalance, then we have to think of something else like imputation or artificial, not imputation, artificial data generation, etc. Okay. So we may also want to see if the data set is balanced or not. So any idea how we are going to do that? Which can we do any visualization to find out whether the data is imbalanced or not? Yes,
Pie chart.
pie chart, absolutely right. One second, where did it go? Can do a pie chart. So we want to do a pie chart on machine status. Do an occurrence count. And this data being a fairly kind of prepared data. So these kind of data which are taken from Kaggle and all, they are already prepared data, and many times these data are also artificially generated data, not real data. That's why you see such clean data. Okay, in reality, that will never be the case. In reality, usually one of the classes will be a rarer class. Number of times the machine is going to fail will be much less than the number of times the machine is not going to fail. Okay. If machine is failing 50% of the time, you know what is going to happen to your production, right? So this is never going to be a real case. Okay. In real case, your failure percentage will be much less. To what extent data imbalance? First of all, why is data imbalance a problem? By data imbalance, I mean that one of the classes is a rarer class. And usually the convention is that if it's less than 20%, it's considered to be a very rare, considered to be an imbalanced data. So let's say that machine failure is 10% and machine non-failure is 90%. Why is it a problem? Anybody? See, these are the things that as domain experts is more important for you to know rather than the theory and the mathematics and the statistics behind the models. Okay, because those are something that is a job of a core data scientist. That's what not you are going to contribute. But these concepts are more important because this is where you have to contribute, and will come to the contribute, and you have to take certain decisions, etc. And we'll come to some of the decisions that you as business experts or domain experts have to take. So what is the problem of a imbalanced data set? Why is imbalanced data set a problem? Yes. Anybody? Very low response today. Yes. Yes. Sorry. Please go ahead.
High cardinality in the model.
No. High cardinality in the model is a different thing. High cardinality of a model is, high cardinality means that a particular feature has a large number of possible values. Let's say roll number of students. So every student has a unique roll number. So if I have my data set consists of 1,000 students, there'll be 1,000 roll number. And hence, it will be futile to find out any relationship between roll number and anything, any outcome. For example, marks or pass and fail. Because if there are so many different values of roll number, there are unlikely to be a relationship. As opposed to, let's say, I have a data about number of classes attended versus the marks. So there are less number of values. Some people have attended all, let's say 16. Some have attended, or even I can group it together. Some people have attended 16 to 20, 12 to 16, like that. So you have less number of values, and it's rational to find a correlation. So that's called cardinality. Here it is not about cardinality. Here it is that when a user is, when the model is trying to find out a pattern, it requires enough amount of data to find that pattern. Pattern between a relationship between the features and the outcome. It's trying to find a pattern, right? Derive a pattern, because I don't know the formula. I have not been able to give a formula that if the radiation leakage is more than 10%, then the machine is going to fail. So I've not been able to give that formula. So it's trying to derive that pattern from the data that I've given. But it can derive the pattern only if it is able to find enough number of data. That is the problem of class imbalance. In class imbalance, one of the classes might have a very low number of data, which is not good enough for the algorithm to train a model on. Concept clear, everybody? Yes or no?
Yes, sir.
Okay. So again, there is no hard and fast rule, or no scientific rule, but the convention is if one of the classes is less than 20%, then it's considered to be a highly imbalanced data. So let's assume, and in most of the cases, the data is likely to be imbalanced or close to imbalance. As I said, because one of the classes, machine failure, will obviously be much less than the number of instances where machine did not fail. So when you have a scenario when you have imbalanced data, as a business user, what will you do? Because why as a business user is important? Because the data scientist will always say, give me more data. That's what they're bothered about. If you say there are only 10% machine failures, they'll say, okay, give me at least data set where 50% machine has failed. Only then I'll be able to work. I cannot work with this imbalanced data. That's the first thing they're going to come back and tell you. Now, your natural failure rate of the machine is 5%. For the purpose of this project, you cannot deliberately make the machine fail. What is going to happen to your production? You cannot say, oh, we have a project, so where we are trying to predict machine failure, and we need to collect more failure data. So this shift let 50% of the machines fail. Can you do that? You can't do that, right? So what will you do? The data scientist had come and told you, give me more data. Otherwise, I can't. It is your ask that you want to predict whether the machine is going to fail. I need more data from you. Give me more failure data. Non-failure data I have enough. I need more failure data. Unless you give me that data, I cannot work. And your management is saying, why is it not that you are not progressing? What is your problem? Give failure data. What will be your answer? And what will be your solution? Yes. Think. Okay. No. No bright ideas? Come on, you are domain guys. Okay. So what is your objective? Your objective is to get more failure data, right? So let's say you have collected last 6 months data. In last 6 months, one particular machine who were trying to predict, in last 6 months, it has failed 10 times and it was working fine 1,000 times. And the data scientist says the highly imbalanced data is only 1% of your data is belonging to the class failure class. So I at least need 200 or 500 failure cases to build a model. So you have only 10 failures, but at least I need 500 failure cases. What will you do? What are the options you have? Yes. So one option is that instead of 6 months, you collect the data for 2 years. So in 6 months, you have 1,000 failure cases. Okay, let's assume that you have got, let's say, 100 failure cases and 1,000 overall cases, 900 non-failure cases, just to make it more practical. So in 6 months, you have got this data. In 2 years, you will get 400 failure cases and 4,000 non-failure cases. Am I making sense? Yes or no?
Yes,
You
sir.
just extend the timeline. You collect data from a longer period of time. So first thing is that you have to set the management expectation clearly that, look, very nice. We have got your own expectation also that we will build this model, but it will take 2 years to take this build this model because we need enough failure data. But what happens at the end of 2 years? At the end of 2 years, you still have 10% failure rate, 4,000 non-failure and 400 failure. Again, that is a likely imbalance, is an imbalance. So again, there's a problem in the model in terms of getting trained. Because the imbalance percentage is still the same. So it doesn't solve your problem fully. In absolute numbers, you increase your failure cases, but in relative numbers, percentage-wise, it's still the same. Okay. So what is the next step or next option? The next option, you can say that, look, what I'm going to do is 6 months I've collected both failure and non-failure cases. I've got 1,000 failure and 1,000 non-failure and 100 failure cases. Next 1.5 years, I'm only going to collect the data of failure cases. I'm not going to collect the data of non-failure cases. Only when the machine fails, I'll collect that data. So at the end of 2 years, I will have 1,000 non-failure cases and 400 failure cases. My data becomes balanced in percentage terms. Will it work? Yes or no?
I think no, sir.
Why not? You're
Because
right, but
again,
you-
data,
yeah.
again, data
Yeah.
is unbalanced. Like because
No, data is not imbalanced now.
because
So
only
first 6 months, I have collected both failure and non-failure cases. I have 1,000 non-failure cases and 100 failure cases. Next 1.5 years, I do not collect the non-failure cases anymore. I just collect the failure cases. So over a period of 2 years, I get 400 failure cases. And because I've collected the non-failure cases only for the first 6 months, I have only 1,000 non-failure cases. So the end of 2 years, I have 1,000 failure cases and 400 non-failure cases, 40%. So the data has now become balanced. Correct, yes or no? Have you got my point, Dinesh?
yes, sir. Data is balanced, but the
But-
timeline is not correct.
Timeline is not correct, means not the same. It's not the same timeline where you have collected failure cases versus non-failure cases. What is the problem if the timeline is not the same? If the timeline is not the same, certain other parameters might have changed. For example, the age of the machine has changed. So you are not collecting the data in a situation where both the conditions for failure and non-failure, all overall conditions are the same. This particular concept is called data drift. your data has drifted. The failure data has drifted from the time when you collected both failure and non-failure data. Data drift will make your model incorrect. So what is the next solution? You still need, let's say, 1,000 failure, non-failure and 400 failure. That's what your data scientist says. At least, look, at least you have to give me this breakup. Fine, I'm giving you 2 years time. And at least you have to give me this too. Give me the data in this format. What is the next solution?
Randomly removing non-failure cases.
Very good. So I have to make I will collect 4,000 non-failure cases, but I'll make a sample of 100 failure cases, 100 non-failure cases from those 4,000. Not 1,000, 1,000 non-failure cases from that 4,000 non-failure cases. Now I have to ensure that the sample that I have taken represents the population. Those of you who are from quality would know how to do this. What kind of test you will do to prove that the 1,000 sample that you have taken out of 4,000, it truly represents the population of 4,000. Otherwise, not going to work, right? 1,000 maybe for the first 6 months only. It must truly represent the population. Only then you can manage the data drift. How will you prove that? Which statistical tool you are going to use? No? You have learned about Z-test, T-test, U-test. What type of test you should use? Okay, let me give you option between two, Z and T. Which one you should use? Z-test or T-test? Oh, okay. You will use Z-test. This is one of the important use cases of Z-test. Z-test is used. Z-test is assumes that you know the population data. T-test assumes that you don't know the population data. Here you know the population data. So Z-test is used to find out if the sample is a true representation of the population. So this 1,000 that you have collected is a true representation of a population. You need to apply Z-test to figure that out. Z-test statistician will apply, but you need to know the concept, because otherwise what will happen is that you won't be able to find out a solution. Data scientist has come and told you that I need this 1,000 non-failure and 400 failure. You don't know what to do. Okay. Now, suppose the management says that no, 2 years is too long a time. I mean, how can you take so much of time? You have to still finish it within 6 months. What do you do? No. This is where you have to prepare synthetic data. These are last option. Always remember synthetic data, and these days, of course, with generative AI, it's becoming more and more feasible to have synthetic data. But this is the last option. That if I do not have enough data, if I am not able to increase my timeline for any other constraint, if I'm not getting the sample, the only option that is left with me is the synthetic data, is generating the synthetic data. provided you still consider that that particular attribute is having a relationship with the outcome. Now, at this stage, the domain expert can say that, look, it is not that important a factor. Probably it has some input, but it's not that important a factor. In that case, you may remove that attribute, but then the problem is that still your problem exists, because what about the other data? Okay, so in this particular case, it doesn't really solve the problem. It solves the problem if you have a lot of missing data for one particular attribute, but if all the attributes have do not have enough data, then you can't take this approach. So far, fine, everybody? Concept clear? Yes or no? Everybody clear? Yes or no?
Yes, yes.
Okay, great. Okay, so also we said that we'll do a correlation. Near correlation. Here all our data is numeric. No, not all are numeric. There are some categorical values as well. Good. So we'll do a correlation on only numeric values, of course. So by the way, categorical values, I hope all are string. Let me see. Yeah. And by the way, we also have to do one more thing, but that we can do later. We also have to take out the machine ID. Machine ID which should not be used because it's high cardinality. It should not be used to predict the outcome. Okay, that we can do after this step. So we don't want correlation with machine ID. We don't want with any of these qualitative values. Also, of course, we don't want correlation between with the outcome. We need the correlation between the features. This is the correlation matrix. And so just a recap, because this is always confusing. So what will the p-value mean? If the p-value is less than 5%, then what will mean? If the p-value is more than 5%, what will mean? So where is less than 5%, we can see the correlation value is higher. Okay. So what is the null hypothesis here? The null hypothesis is that anybody? What is the null hypothesis here? In simple terms, actually null hypothesis you have to frame where something is equal to something. Okay, but in simple terms, what is the null hypothesis here?
In this case, it is accept the null hypothesis.
But what is the null hypothesis? Unless
The
you
age
frame the null hypothesis, if you say accept or reject, it may just be the other way around, right?
age of the machine is directly linked to the other attributes.
not other attributes. So here we see when we talk about this age of machine and days since last repair or whatever, last service. So the null hypothesis is that they are not correlated with each other.
Yes.
So null hypothesis is not correlated with each other. Why null hypothesis is not correlated with each other? We know that where they are correlated, the correlation value is high. And where the correlation value is low, then the p-value is high. That means the null hypothesis is that they are not correlated with each other. The p-value will be high. If the p-value is less than 5%, that means the null hypothesis is rejected and hence they are correlated with each other, as in the case of radiation leakage and pressure bar. In this case, we reject the null hypothesis that they are not correlated with each other because the p-value is less than 5%. And obviously, there is a case for looking at these two features because these features may outweigh, if both these features are present, these features may outweigh the other features. Again, the domain expert will come in. So the first easiest method is to remove one of them. The domain expert will come and say that is radiation leakage likely to have a more impact or pressure bar likely to have a more impact as per his or her engineering knowledge. Depending on that, one of them will be removed. And of course, if that is not the case, if both are likely to have equal or similar impact, then we have to find out a artificial measure which will incorporate both radiation leakage and pressure bar. Maybe a product of the two values. That's the easiest way. If the two dimensions are different, you make a product of that and radiation leakage multiplied by pressure bar and create an artificial measure that incorporates both radiation leakage and pressure bar and act as one feature. Correct? Concept clear? Yes or no? Okay.
Okay, sir.
Great. So assuming that right now we are not doing any pre-processing in terms of removing these kind of features or data set is already balanced. So we'll straight away will not use this EDA to take an action. In normal circumstances, probably we'd use it for where the correlation is high, etc., etc. We will use this column filter to take away the high cardinality values. Take this out. Okay, so we don't have it. Normally for logistic regression, after this, we apply a normalization. So two things we apply actually. If we had to use logistic regression, we had to convert the categorical values to numeric values through one-hot encoding, and then we had to normalize both these, all the values, all the numeric values. Would we do the same thing for decision tree? One-hot encoding and normalization. Would we do the same thing for decision tree? Yes or no? Yes, everybody is quiet. Logic, apply logic.
Likely, yes, because we'll have to bring everything in the same units or same scale.
No. No, incorrect logic. See, data science is very simple. Analytics is very simple. It's pure just logic. Most of us are engineers, right? All that we have to do is to apply plain and simple logic. See, in logistic regression, why did we have to normalize? And why did you have to have numerical values? Two things. One hot encoding converts any categorical value to numerical value, and normalization brings to one scale. Okay. Why did you have to do this? Because logistic regression is a variation of regression. It is an equation. Y equal to function of X. Can I have an equation? Can I have a mathematical equation with non-numeric data? The answer is no. Equation is with numbers. Okay. Equations were studied in the subject of mathematics, not in the subject of English. Though these days with text analytics, you have equations. You can have equations with words as well. Okay. That's the concept called word to vector. But I'm not getting into that. It's a part of text analytics. So today's, all this large language model, all of them work on converting English to mathematics. Okay, but that's a different thing. Otherwise, normally you have studied equations in the class of mathematics, where we had equations. Many of us used to fear that. And in the class of English, there was no equation. So those who are not good in maths, they were enjoying English. Okay. So equations can be drawn only when it's a numeric value. And that's why we're forced to use convert categorical values to numeric values. And because these numeric values can be in different scale, if we don't normalize them, those which are in the bigger scale or larger scale will have a more dominant influence on the outcome. So that's why you normalize. What is decision tree? We are moving from mathematics class to logic class. Decision tree is about the logic class. Okay. If there is cloud cover, it will rain. If there is sun, it will not rain. It's logic. There is no mathematics here, apparently. Logic class doesn't have need any equation. Right. Because it doesn't need any equations, it is more like if else. If this happens, if the age is less than 15 years, 20 years, they will use Pokemon Go. If the age is more than 20 years, they may use Snapchat or WhatsApp. But if the age is more than 20 years and if the user is male, they will use Snapchat. If the user is female, they'll use WhatsApp. It's if-else statement. It's logic. Okay. In competitive examination, CAT and GMAT, this is the logical reasoning portion as opposed to quantitative aptitude portion. One portion takes your mathematical ability, other portion tests your logical ability. Decision tree is about logical ability, logic. So if it's logic, then there is no question of converting it to an equation. And hence there is no question of converting everything to numbers. Let numbers remain numbers and categorical values remain categorical values. In fact, categorical values, the logical reasoning is easier because there are only finite number of if statements that I can create. If there are male and female, there are only one if. If it's male, then what happens? If it's female, what happens? Else what happens? But it's age, which is continuous number, there can be many if. If less than 20, what happens? If more than 20, what happens? Within less than 20, with less than 15, what happens? If 15 to 20, what happens? And it can go on. But net, I don't require to convert all my features into numeric value. Because it is if-else, less than 50, more than 15, more than 15, height is less than 1.5 meters, more than 1.5 meters. This logical statement does not depend on scale. In one case, it is 15, 20, 25, 30. Another case is 1.5, 1.8, etc. Doesn't matter if the scale is different. So both these activities are not required, both these steps are not required when you are using decision tree. Concept clear? Yes or no?
Yes.
Yes, sir.
So good thing is that we can straight away now go to partition. Okay. Between the test and the training data. So when you say relative size, so he's saying 70% of the data will be one data set, which we will be using for training. Usually the larger sample we use for training and the smaller sample we use for testing. So 70% data we'll use for training, remaining 30% we'll use for testing. Anybody remembers what type of sampling we used in case of regression? I think this I also mentioned this in logistic regression. Same thing, rule applies in logistic regression. Okay, but logistic regression you have to convert numeric to category to numeric, and you have to normalize. But sampling, the difference between regression and logistic regression exists, but logistic regression and decision tree are same. Sampling methods are same. What is the sampling method that we should use? Who remembers?
Stratified.
Stratified. Very good. Why not random? Why random can be used in regression but cannot be used for classification?
Because here the output is yes or no, or whereas in regression it's a number which we are predicting.
It's a continuous number. Okay, and it is the sampling. The has you don't have to consider any class while you are doing a sample. But here, both the samples, the training and the test data samples, they should represent both the classes in the same proportion as they are present in the population. That's why we have to have stratified sampling. And on what basis I'm going to do stratified sampling? Last time there was only one option that was available, which is machine status. But this time it is giving me all options because this stratification can be done only on categorical values, not on numeric values. Last time in logistic regression, all values were converted to numeric values except machine status. Because before that only we have done one-hot encoding. But now we have not done one-hot encoding. So the categorical values have remained categorical and is showing on what basis. So obviously we have to do it on the basis of the outcome that we are trying to predict. And we know why we need a random seed, so that every time I run the pipeline, the training is done on the same data set. Because even though I have done stratified sampling, those individual observations that has gone into training and those which have gone into testing may vary if I do not have a fixed random set. So every time I run the pipeline, it may give me a different result. Okay. So far fine. So apply and execute. So I have one data set of 337 values, another data set of 145 values. Okay. So now at this stage, I am going to use the decision tree. We'll use decision tree learner and decision tree predictor. Now there are a few important configuration elements that are coming up. Understand this concept carefully. First of all, what is the class which we are going to predict? Is machine status, right? This is, so as you can see, it is giving me all the other categorical values, but we are going to predict machine status. Now there is something called quality measure. Quality measure is the metric which the algorithm will consider while it is trying out different iterations of making the decision tree. Remember with the simple example that we had where we tried to predict the app, there were two different approaches. One approach is first make a decision tree, branch a decision tree based on gender. And the other approach was first branch the decision tree based on age. And we saw that if we branch the decision tree on base of age and the right, because age is a continuous value, we have to branch it at the right point. If we branch less than 10 and more than 10 years, then our results would be different. We have to branch at less than 20 or more than 20. And if we branch by age and age less than 20, more than 20, we can arrive at observations which has the lowest entropy. That means the purest form of classes in the shortest possible route. Now, obviously, when we have many more observations and many more attributes, you cannot achieve the shortest possible route in one step. The algorithm has to iterate multiple times before it arrives at the shortest possible. Okay. And how does it know that it arrived at the best possible route? That is defined by this quality measure. There are two types of quality measure, gain ratio and Gini index. I think I've explained this in the last class. Just confirm yes or no. If not, I'll try to explain again. As far as I remember, I have explained this. I might be incorrect. Because there are other courses going on, so it's possible that I might have missed out, confusing with other courses. Did I or did I not? Yes or no? Or nobody remembers? If nobody remembers, then it makes sense to repeat it.
Last class we didn't attend it, sir.
Okay, somebody would have
Better
attended. Some people among this group would have attended. Okay, if nobody's attended, then probably I'll repeat. Anybody remembers? Yes or no? Anybody attended and remembers? No. Okay. So I think we'll repeat it, but I'll come to that later. Okay. So for the time being, just part what is meant by Gini index and gain ratio, and we'll come back to this. Okay. You have something called minimum number of records per node. Okay. What does this mean? Okay. Now this has to do something with the Gini calculation of Gini index and gain ratio, but I will come to these calculations. These are two formulas: Gini index as a gain ratio as a logarithmic scale, Gini index as a simple scale. Okay, so there are some formulas. Basically, these are formulas to calculate entropy. Entropy we know is disorder, right? So whenever you are doing a classification, you need to ensure that the when you're branching off and putting into classes, you have as far as possible observations belonging to one class only. So if 100% of your observations belong to one class, let's say machine will fail or not fail. Let's say I have 20 observations That's when I say that radiation leakage is less than 10%, the number of failures, all the observations show that the machine did not fail. And when the radiation leakage is more than 10%, all the observations show is belonging to the class machine fails. Then we're 100% sure that if radiation leakage is less than 10%, machine will not fail, and the radiation leakage is more than 10%, the machine is going to fail. That gives me the maximum confidence. This maximum confidence, that means when there is no impurity, no mixture. It's different from saying that if the radiation leakage is less than 10%, 60% of the machines do not fail, but 40% of the machines fail. Then I cannot say with certainty that radiation leakage less than 10% will mean that the machine is not going to fail. Because 60% of the cases machine does not fail, 40% cases machine fails, which is a very significant number. Correct? Yes or no? Just but clear, yes or no?
Yes, sir.
Great. Now tell me one thing, think logically. If I allow the decision algorithm to branch the if-else statements in whatever way it is possible, there is no restriction. What is likely to happen? I give no restriction in terms of the number of branches it can make and number of times it can make the branch. Only thing I'm telling the model that you have to ensure that the entropy of the disorder is lowest. That means at the end of the branching, you must arrive at a situation or as a set of observations which will be either machine failure or not machine failure. There'll be no mixture, because that's what I want. I want to be confidently saying that the machine is going to fail or not fail. To do that, I need to arrive at a set of observation which is 100% machine failure or 100% machine not failure. Okay. What will the algorithm do? No idea? Just think logically. The algorithm has been allowed to write any if-else statement, any logical statement, till it arrives at a point, and there are two classes, machine failure and non-failure. It arises a situation where every logical conclusion has to conclude either a machine is going to fail or not fail. In that situation, what is the minimum number of records per node? What is a node? When you have a decision tree, when you are branching the decision tree, the last point of the decision tree, those are called the leaf nodes. So what is the minimum number of observations each leaf node can carry? No idea?
Hello, Professor. I joined late.
Yes.
Yeah, according to me, I think the decision tree or the node will take the maximum number of line items, what the number of features we have given.
Number of line items?
Number of lines, yeah. For example, I have fed maybe 50 different.
Okay. So the minimum number will be 15, you are saying?
Yeah.
No, there's nothing to do with the number of features. The leaf node will carry. Okay, let me do one thing. I think it will be difficult for you to understand it like this. What I'll do, I'll run the decision tree. I'll show you the decision tree and then I'll ask you the same question. For now, I'm just giving a number 20. I'm not explaining why I'm giving the number 20. Okay. So I'm just running the decision tree learner, and I'll show you the decision tree, and then I'll ask you the question. First, I'll explain what the decision tree looks like. So are you able to see a pop-up screen? Yes or no?
No.
Showing the decision tree? Okay. Okay. So this is the decision tree. Now you're able to see?
Yes.
Okay, great. So this is the decision tree that the algorithm has created after multiple trial and error. It has already done those trial and error, and this is the most efficient decision tree it has created. What we mean by efficiency? We mean that this requires the least computing power. That means it reaches to the conclusion the fastest possible route, as well as where the disorder is minimum given certain constraints. Okay. Now understand what the decision tree means. First is the data set that we have given. For the training data set, we have given 337 records, out of which 0 class is 169 and 1 class is 168. So we know that it's stratified sampling, and our data set is a absolutely balanced data set. Probably it's an artificially generated data set. 50% are machine failures, 50% are machine non-failures. So that's why the sample also has 50%. Now it has figured out that out of all the parameters, on which parameter it should branch first to get the most efficient decision tree. That's the iteration that is done. It's equivalent to iterating between age and gender, which we did manually. And it has figured out that the first point of branching to make the most efficient decision tree is vibration level. And it is branching saying that if vibration level is less than 4, whatever is the unit of measure, we don't worry about the unit of measure here, less than 4.005, what happens? And if the vibration level is more than 4.005, what happens? Why it has taken 4? That also through iteration. Just like we identified less than 20, more than 20 in case of age, it could have been less than 15, more than 15, could have been less than 30, more than 30. But because the data set was small, we could easily figure out that if it's less than 20 and more than 30, we are able to bifurcate the two classes very cleanly. But here the data set is much longer, and it has done its own iteration to figure out that it should branch at 4.005 and not at 3 or not at 5. Up to this clear? Concept?
Yes.
Yes or no? Yes?
Yes, it's clear.
Yeah, sorry, any question?
No, it's clear, Professor.
Okay, great. So it is saying that when the vibration is more than 4.005, it has total 74 observations where the vibration was more than 4.005. Out of 74 observation, 17 observation machine did not fail, and 57 observations machine failed. That means there is a 77% possibility or probability to say that the machine will fail that if the vibration is more than 4.005. Now, is 77 probability good enough for us to say that moment the vibration is more than 4.005, machine is going to fail, stop the machine? Probably no. Probably would have liked if we could get a probability 95%. Only when we see that the probability of the machine failure is more than 95%, we'll take action. 77% is not good enough for me to take the action. So ideally, I would have liked that the model to branch further, take one more attribute and then again branch further and get me a higher percentage, which it has, for example, done in the other case. In the other case, what has happened? If the vibration is less than 4.005, it is saying that there's a 57% chance the machine will not fail, and there's a 42% chance the machine will fail. But it's saying that I can give you more information from where you can get more confidence, you can gain the confidence if you allow me to branch further. And when I branch further, I'm taking the next attribute, which is usage mode. And I'm saying that if the vibration level is less than 4.4005 and the usage mode is idle, that means the machine has not been used for a long time, then the probability the machine is not going to fail is 72%. Otherwise, it is 27%. Again, you may say that this is not sufficient. Okay, but what about this? You see that if the vibration level is less than 4.05 and the usage mode is high load, then there's 64% probability the machine is going to fail. There's 35% probability the machine is not going to fail. And the model says I can give you more confidence and say that if the vibration level is less than 4.005, the load is high and the voltage fluctuation is less than 1.345, then there's 90% probability the machine is going to fail. And probably at this point, you are satisfied that, yes, now I can say that machine is definitely going to, the high chance the machine is going to fail. Let me stop the machine. Up to this part clear? Yes or no?
Yes, yes.
Now, obviously, you would have liked same kind of decisiveness. Let's say 90% is the minimum that you want in the other cases as well. You want that level of decisiveness for the model to tell you whether the machine is going to fail or not. And for you, let's say the cutoff is 90%. Then why didn't the model not able to reach or give you that level of confidence? Because of two reasons. Possible two reasons. One reason is that if you branch this further, there is no information gain. Information gain means at least one of the branching nodes should have a probability of one of the classes higher than the probability of the same class in the upper node. So if the probability of one is 42%, one of these nodes must have the probability of one more than 42%. If it is not, then there is no point in branching further. Either 1 or 0. One of them must be greater than what is there in the previous node or upper node. This concept is called information gain. It will branch till there is an information gain. So far correct? So far understood? Yes or no?
Sir,
Yes.
what is this
Decision-
total it is showing?
Total is the total number of observations in this node. That means where the vibration level is less than 4.005, there are 263 observations where the vibration level is less than 4.005.
78%? What is this?
So
78?
that's the 78% of the total observation. Total observation 337.
Okay,
Out of that,
okay.
263 observations is less than 4.005 and 74 observations is more than 4.005. That is 22%. So 78%, 22% would be 100%. This 100%.
Okay.
And within this 263, 152 observation the machine has not failed, and 111 observation the machine has failed. Correct?
Correct.
So, given no constraint, the model will keep on branching till there is an information gain. In such a situation, now these are called the leaf nodes. The end nodes are called the leaf node. This is a leaf node. This is a leaf node. Okay, ends are called leaf node because it's a tree. So leaf is at the end of the tree. Question is, what is the minimum number of observation? This number 74, 260. What is this minimum number that a leaf node can carry if the objective of the decision tree is to have information gain and there's no constraint in terms of branching? What is the minimum number of observations that a leaf node may have if the objective of the decision tree is to gain information without any constraint? Without any constraint on the number of observations in the leaf. You are saying that you can have as low a number of observations in the leaf, but you get me the highest information gain. You get me the highest level of confidence that here I got 90%, I want to reach 100%. I should be able to predict or get whether machine is going to fail or not fail. Either case, I want to get to a state where I will be able to predict with 100% confidence. In such a scenario, what is the minimum number of observations we'll get in the leaf node? Logical question? Yes. Huh? Two?
Yeah.
Why two?
Because since we have not defined any numbers, a minimum number
Yes.
can be 2 because it can start the category maybe either failure or not.
Yeah,
failure.
but then
So with the two
yeah, but then if it's 2, then that one value can be 0, another value can be 1. But I want 100% confidence. Now, if one value is 0 and one value is 1, then I'm only 50% confident. Think one step ahead. What will be the minimum value to get 100% confidence?
Then it is 1 reading.
Then it's 1. Everything is logic. Very simple.
I mentioned 2 because it should be if or else, so there should be at least 2 reading to compare.
Okay, so
that way I
you're
told,
saying
yeah.
that in one branch that can be 1, another branch that can be 1. That is right.
Yes, yes.
Yeah, that way right. Yes. But in one leaf node, the minimum can, if that is the objective, the decision tree will try to meet that objective. It will break down till it will make more and more branches like it has done here. It will make more and more branches till it comes to a point where each of these leaf node will carry only one observation, because with that one observation, you are 100% confident that whether a machine will fail or not fail under those conditions. My next question to you, is this the desirable outcome? Where leaf nodes may contain one of observations, many leaf nodes, if not all.
No.
No. Why not?
Because then it will not give me the direction in which I have to take a decision. Because every node means there will be multiple options available. So
it
is
will
like
give me the direction. Yeah, not multiple option. Assume that this value is 100%. Okay, it has given me, I may have to create multiple if-else condition. If vibration is less than 4.00, if usage mode is equal to high load, and if voltage fluctuation less than 1.0, like that, I have to make a long if-else statement. But ultimately, I'll get one if-else string, where I will say that 100% the machine is going to fail. It may be very long, but there is a definite series of if statements which will lead me to conclusively say whether the machine is going to fail or not fail. And if I look at it, that's what I actually wanted. So what is the problem?
The problem will be, for example, I get many number of outcomes based on
Yeah.
the features. So then,
I get
if,
a large number of leaves, right? That's what you're saying.
yeah, yes,
So it may be manually analyzing that may be complicated, but I'm not going to anyway manually analyze that. I'm going to, when I use this model for testing or for actual outcome, I'll give a data and the model will anyway give me the output. The model will pass that data through this branch. I don't have to manually pass this data. If I have to manually pass this data, what you're saying is that I get a data set, I have to figure out that whether the vibration level is less than 4.0 or more than 4. Then I have to figure out whether is then for human, this may be very complicated, but I am not doing it. I will pass that value and the value will be passed through the model and the model will tell me after passing through this if-else statement, whether the machine is going to fail or not.
but the result may not also be right.
Why?
Because each feature based on which I am taking a decision. So the number of data required is not sufficient, maybe because it is giving the outcome based on only one input.
No,
Or
not based on one input. So training has been done.
There's too much of variation in the data also.
Okay. Okay. We have heard about something called overfitment.
Yes.
What is overfitment? Overfitment means your training model is too much accurate to give you a very high variance and low bias. If the data follows exactly the same pattern as given in the training data set, you will be 100% correct. But if there's a slight variation in the pattern of the data, which you want to predict, compared to what data you have trained the model on, your model will be totally haywire, which we don't want. In regression, this was equivalent to the degree of polynomiality of the regression line. If we do not give any constraint on the degree of polynomiality, the model will eventually find out a degree of polynomiality where the line will pass through individual points. And the R-square value will be equal to 1. The model will be 100% fit. There will be no error. There will be no unexplained variation. But that is not the best model, we said, because it's an overfitted model. It will not be able to predict if there's a slight variation on the actual data that is coming for prediction with the past data. In decision tree, having a leaf node equal to 1 is equivalent to overfitment. It will give you the least error for the training data set, but when you are predicting for a new data, it will give you erroneous result. Concept clear?
Yes.
Okay. Now, if you see that instead of 20, if I make this 5, what happens? Instead of 20, if I make this 5, number of branches will now go up. Last time, if you remember, when it was greater than 4.005, it stopped at this. Now, Now, when I've allowed a lower number of leaves in the node, it has been able to find out the path of information gain, which is saying that if the vibration level is greater than 4.005 and the voltage fluctuation is less than 2.3, there is 90% chance that the model will fail. And is further, it can break down. There will always be an information gain when the vibration voltage factor less than 2 and the location type is rural. I'm 100% certain that the model will fail. So it has reduced its bias, but probably it has increased its variance. Because the model is trying to go towards more accurate side, hence to overfit. Now you may ask the question that should I use 20? Should I use 5? Should I use 30? How do I know what value I should use? There is no way of knowing that except trial and error. And that is why you have to do multiple trial and error with different values of different values of different parameters, experimenting with different values. Try with the train and test, try with train and test, and see when you get a bias variance, balance between bias and variance. Is it possible to do humanly? No, it will take a lot of time. That is where something called automatic ML or auto ML comes in. There are platforms like Azure or AWS, SageMaker, which allow you to do auto ML, which will do its own hyperparameter tuning and arrive at the balance between bias and variance. Concept clear?
Yes.
Great.
How do you know that there's a balance between bias and variance?
So there is a mathematical formula based on which you can calculate what is the balance between bias and so you can calculate variance, you can calculate bias, and you see where the balance is. And you don't have to calculate. The algorithm will calculate the bias and the variance for each of the iterations and come to a point where bias plus variance is minimal. So none of these things need to be manually calculated. Okay, only the concept needs to be understood because manually, how many times you will calculate? So these auto ML packages will do this and give you the final decision tree that has already balanced the bias and variance. You don't have to worry about it. Okay.
Yes.
Great. So when we talk about this Gini index or gain ratio, you are actually calculating the amount of disorder through a mathematical formula in each of these leaf nodes. So the amount of disorder is minimum when it is there is no impurity, like we saw here in this particular node, where it is 100% probability that the model will that the machine will fail. There is no impurity. Entropy is 0. Right. And where the entropy, where it's 50-50, almost 50-50, the entropy is the highest. Here also you see where it is urban. Okay, there's 100% probability the machine will break down if the voltage is less than 2.3 and the location is urban. So whether the location is urban or rural, if the voltage is less than 2.3, the machine will break down. But when it is semi-urban, that's when it looks at the next category, which is pressure bar. Now, again, it cannot go beyond this because I have said that you cannot have any leaf node where the number of observations is less than 5. So it's working on two constraints. One constraint is it can break down to the next level of leaf nodes if there's a gain There is information gain. That means that is one of the node must have a higher probability in one of the classes or one of the classes. Second constraint is the total number of observations cannot fall below the minimum number of observations that we have defined in the leaf node. So even though here is 60-40, and even though there might have been a possibility of information gain, if it was broken down further, it is not able to do that because it reached the minimum number of leaf nodes. Correct?
Yes.
So the amount of disorder, that is the measure of how efficiently or what is the path it will take to branch. So right now we are seeing the final path of branching, final branch. Before that, it has created hundreds of iterations of different paths of branching. So every time it has calculated this measure of either Gini index or gain ratio to figure out in which path it is getting the maximum gain. We'll talk about the exact formula later on. Okay. But first, let us complete this so that we understand the process, and then we'll talk about the exact formula of Gini index and gain ratio. Again, that even if I don't, as a business user, even if I don't know the formula, it's fine. The statisticians handle that. I must know the concepts so that I can contribute at the right places. I should be able to say, look, this is my domain. Okay, let me give you the inputs on this. And then you proceed. Okay, I should be able to intervene where I think it is my call. It is, as a domain expert, it's my decision on a particular matter. So I must know where are my intervention as a domain expert required. Where is not required, I'll allow the scientist or the statistician or the software guys to take over. But not in all the places. Not like, okay, I have a machine learning problem. Now, IT guys, you do everything. I don't know anything. Okay, so coming back. Now that we have, let's complete the cycle and then we'll talk about the formula. We have the decision tree learner. So we'll take the decision tree predictor. Rest of the process is very similar to our logistic regression. We take the model, except the fact that in case of logistic regression, the model was an equation. We had the coefficient, we have the intercept. We also had the p-values to determine that which variables have an impact and which variables don't have an impact, etc. In case of decision tree, it is a if-else condition. Okay. So it's not an equation. So we'll take this. Okay. So here I'll just change this is something that we have done, same thing as we have done in the logistic regression. We'll say predicted failure. We'll say append columns. Okay. Execute. So now we have the probability, and accordingly, the probability of machine not failing, state is equal to 0, probability of machine failing. So these are complementary. So if this is 1, this has to be 0. And then depending on which class, so if I say that, I'm taking the class 1 as so 1 as failure and 0 as non-failure, accordingly I will get. Okay, so here, for example, actual output is machine will not fail. Predicted is also machine will not fail. Here, for example, machine will fail, but the predicted outcome is machine will not fail. Okay, so like that, we are getting these values. And now we need to calculate the score. So what kind of scorer we should use? what is the parameters that we'll check to find out whether the the accuracy of the model, the efficiency of the model?
Numeric scorer.
No, numeric scorer is for R square. This is not
Ah.
numeric scorer. Here we have to get confusion matrix. So we have to use normal scorer. Okay. Sorry, you can't use I took numeric scorer only. So it came like that. Okay, so the first column, that means we are comparing against machine status, and the second column is predicted failure. Okay, so machine status versus predicted status, whatever. I should have written predicted status anyway. So execute. And now you have the confusion matrix. So in KNIME, the verticals are the predicted ones and the horizontals are the actual ones. So there are 50. So 0 is not failure, 1 is failure. So there are 53 cases where the model has predicted that the machine will not fail and the machine has not failed. But there are 26 cases where the model has predicted that the machine will not fail when the machine has actually failed. There are 19 cases where the model, or 47 cases the model has predicted the machine will fail and the machine has actually failed. And there are 19 cases the model has predicted the machine will fail, but the machine has not failed. And we know the various, we have discussed this already, the various types of statistics in terms of accuracy, precision, and recall and F1 score. Okay, I hope everybody is clear about the formula. Last time we discussed this. So we have got an accuracy of 0.69. You can try out with logistic. I don't have that model here in this computer, so you can try out both logistic regression and decision tree. Usually, when we have only numeric parameters, logistic regression works better. When you have categorical values or a mix of categorical numeric values, decision tree works better, usually. Okay. Well, not as a rule, but as a, not as a formula, but as a more like a thumb rule. So you can parallelly do a logistic regression and find out which model is giving a better performance. So
So the parallel you do means that feature you don't have, we will have that feature.
No, I don't know. What do you mean?
No, you told parallel you
Parallel
can
means
check,
you do
have
logistic
to
regression.
create a one more model.
Yeah, create one more model. So obviously for logistic, we have done that in the previous class,
Yes.
previous class before that. So there we, instead of decision tree, we are using logistic regression. Okay. So you can compare with the same data, you can compare which model is giving you a higher accuracy.
My question is, can we do in the same model regression also from column filter? Can we have a new branch and then?
Yeah. See, this is the canvas. In the same thing, I can parallelly draw. So last class, I think we are discussing that from where we can branch off. So obviously from column filter, we can branch off, and then we have to do these two pre-processing steps, one hot encoding and normalization, and then do table partition, and then regression learner and regression predictor. Okay.
Last class
So
we didn't discuss that.
Huh? Last class, so one of the class. We have done only logistic regression.
Okay.
Yeah, one of the class. I'm not sure.
No,
whether
logistics
last class,
I know,
I think,
not to branch and have multiple models.
yeah, I think that we did in the last class when we just started decision tree. Okay, last class we just started the decision tree up to this week.
Correct.
Okay.
Yes.
So there we actually took a branch from the logistic regression and did this. Okay. In the same file. Okay.
Yes. Thank you.
Great. So I think we'll close here. We'll continue in the next class. Next class, we'll talk about this gain ratio. And after that, we will see how this can be done using vibe coding. Those of you joined little late, vibe coding is coding with the help of prompt. VIBE coding, vibe coding. This is another very important skill that is becoming very relevant for business users. As a business user, I don't need the expertise of a coder to write machine understandable codes. I will write in my own language based on my own based on the business requirements, which I understand better than the coders, and the codes will be automatically generated by GenAI engine. So that is a new expertise that is in high demand. No, is as recent as vibe coding was the term was coined in January or February 2025. So
This is
every
prompt
year
engineering.
it's a variation of prompt. Prompt engineering can be is typically means to it can be used for everything. I can use prompt engineering to generate a quotation or a proposal. But vibe coding is a specific, you can say, a category of prompt engineering used to write computer programs and execute computer programs. So today, enterprise grade apps, applications are being developed using vibe coding purely by business users without any help of any IT team.
Okay.
Full scale enterprise grade applications. It has and the advancement has been in super speed. I mean, probably even 1 year back, nobody knew about it. 6 months back, probably people were thinking of developing a very basic website or a very rudimentary app. Now, full-scale apps, which are running e-commerce apps, things like that, which are doing business on the apps, are being developed completely by vibe coding without a single IT person in the team. Okay, and you can see if that is the situation that has happened in 1 year, in 3 years, this will be the norm, which will be the practice. Okay, so more and more business users are going to play more dominant role in developing technology. Organizations will have a very lean tech team, only consisting of very high-end tech guys. All the low-end tech guys will not essentially have any work. This is where the future is. It is a very scary future for India because we all know that India's large workforce is in IT. You are already seeing the news about large software companies laying off. So it's a very, and we have just a digression. We have probably 1 or 2 generations who have learned only to do coding. They have not gone into core manufacturing. People like you, okay, we have remained in core manufacturing. There are many people who have moved away from core manufacturing and become software developers. Of course, if that was the end of their career, probably they'll not be affected. But if they're early or beginning stage of their career, many of them are going to be affected very adverse. So that's the big shift that's going to happen in a lot of things. You will find people coming back to mechanical, electrical, core engineering companies. A lot of changes are going to happen. Yeah. Okay. Good. So shall we close
Thank you,
today?
Professor. Yeah.
Okay. Yeah. Okay.
Yeah,
Bye.
thank you,
Bye,
Professor.
everybody. Bye.
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 Thank you.
Bye.
Thank you. Bye bye.
Bye.